So we're in section 9.6. All right, so anytime you do graphing, one of the kind of the fallback method of graphing something is making a table of values. So we can do the same thing for polar graphs. So let's do that by graphing r equals 3 cosine theta. So I'm going to grab a piece of graph paper here. And I'm just going to make a table of values. My table of values is going to have theta and r. And I'm just going to plug in some values of theta and calculate r and plot those on my graph. So when theta is pi over 6, I'm just going to plug in, calculate 3 cosine pi over 6, and I get a decimal, 2.6. So at pi over 6, I get, there's 2.6, about there. And when I plug in pi over 4, I get theta, we'll plug it in, calculate, I get 2.1. So there's 2.1. When theta is pi over 3, I get 1.5. So there's pi over 3, 1.5, about there. And then when theta is pi over 2, r equals 0. So I get a point here. Now I'm going to keep going. I'll do the rest of my table over here. Theta r. 2 pi over 3. R equals negative 1.5. So I go here to 2 pi over 3, but I'm going 1.5 units this direction. Um, 5 pi over 6 for theta, and I plug that in and calculate, and I get negative 2.6. So here's 5 pi over 6, negative 2.6, about here. I just skipped the pi over 4 one down here. And then when theta equals pi, r equals negative 3. So there's pi, but I go over 3 units this direction. Oops. And there's my point. And here's my graph. That is a circle with diameter equals 3. And my center is here at 1.5. So it's a circle shifted 1.5 units on the x-axis. So that's the polar equation of a circle. Let's look at this in our calculator. So we had been graphing in parametric mode. Well, I'm going to change my mode here to polar. So I'm going to go down here, go to polar. And now when I go to y equals, instead of y equals, I get r equals.
Is this in radians or degrees?
It would be in radians. So 3 cosine theta, and I'm going to graph that, and there's my nice circle. For this one I did zoom trig for my window. Isn't that nice? All right, questions on that one? Well, just like when we graph in rectangular coordinates, we take advantage of what we know about symmetry. So we know even functions are symmetric about the y-axis. Odd functions are symmetric about the origin. Our conic sections are symmetric about one of their axes. So we know if we know what half the graph looks like, we know what the other half looks like. Well, there's some rules for symmetry that we can take advantage of in polar coordinates that will help us make sketching graphs easier. So let's look at those, and then we'll sketch another graph and use symmetry to help us out. There are two basic rules for symmetry that we will use the vast majority of the time. The graph of r equals some function of sine theta. So that just means that our equation just has something to do with sine theta. No sine squareds, no r squareds, just sine theta. This graph is going to have pi over 2 symmetry. And what we mean, remember what we mean by theta equals pi over 2 is the vertical axis. We call the pi over 2 axis, the vertical axis, the pi over 2 axis. Theta equals pi over 2. So our graph of some function of sine theta is going to have symmetry about the vertical axis. The graph of r equals some function of the cosine of theta. Means we just have a cosine in there, no squares, no tangents, nothing else, is going to have polar axis symmetry. And that's the same as saying theta equals 0 or the horizontal axis. The polar axis is the horizontal axis. So if we go back here really quickly, this is just a function of cosine of theta, and we see it has symmetry about the polar axis. It's the same above as it is below. So if we know what kind of symmetry, if we knew that ahead of time, we could have graphed the top half and then knew the bottom half would be exactly the same. So these two rules we will use probably for what we do about 95% of the time. If you have a more complicated function, there are a few more rules for symmetry that we can use. If we replace r theta by negative r, negative theta, and rearrange and simplify, and we get the same thing. This is going to have pi over 2 axis symmetry. If we replace r theta by r negative theta, do some simplification, and we get the same thing. We are going to have polar axis symmetry. And then the last one we can test for origin symmetry. We replace r theta by negative r theta. We get, and we simplify and rearrange, get the same thing. We have polar symmetry. And by polar symmetry, I mean origin symmetry, because the pole is the origin. Now the first two are what we're going to use 95% of the time. These we're going to use if we have something a little more complicated. And when I say plug in and rearrange and simplify, we're remembering that the sine of negative theta is negative sine theta. Sine function is odd. And the cosine of negative theta equals the cosine of theta. Cosine is even. So this is what I mean when I say we plug these in and simplify. All right, so questions about our symmetry rules. If you remember these two, this is going to get you most of what you need. All right, so let's sketch another graph using symmetry. So let's graph r equals 2 minus 2 sine theta. All right, so this just has a sine theta in it. This is r equals some function of sine of theta. All right, guys, let's stop talking, please. So what kind of symmetry is this going to have?
Vertical, right?
Vertical or pi over 2 symmetry?
Yeah.
So all we need to do is sketch one half, and we'll have the other half. So let's sketch a graph of this thing. Let me get some graph paper here. And we'll make our table of values, theta and r. All right, so when I plug in theta equals 0, here, I get r equals 2. So we had a point here. When theta is pi over 6, I'm just plugging in and calculating. I get that r equals 1. When theta is pi over 4, I get that r equals about 0.6. When theta is pi over 2, I get that r equals 0. So the top half on this side looks like that. And we know it has pi over 2 symmetry, so I'm going to get the other half is going to look like that. But we're not quite done yet. So let's continue our table. I'm going to start down here at 3 pi over 2 and go to 2 pi and graph this half down here, and then we can complete that one. So at 3 pi over 2, I get that r equals 4. We get a point there. At 5 pi over 3, I get that r equals 3.7. So 5 pi over 3, 1, 2, 3.7, something like that. at 7 pi over 4, I get that r equals 3.4. So something like this. And then I'm going to go all the way to 2 pi here. When theta equals 2 pi, r comes back to 2. So the bottom half of this thing looks like this. And the other half is going to look like that. And this is called a cardioid. like cardiac. Cardiac. Has to do with your heart. So yeah, this graph, I'm going to highlight this. This graph is called a cardioid. And let's graph this one in our calculator. So we have 2 minus 2 sine theta. And graph that. And there's our cardioid.
Oh, peach emoji, am I right?
So how would you guess the graph would change if instead of 2 minus 2 sine theta, it were 2 minus 2 cosine theta?
It would just flip
It would rotate 90 degrees. We'd have symmetry this way, and we get a cardioid going the other way. Oops. So there's 2 minus 2 cosine theta. All right. Another tool that we can use to help us make our graphs is knowing when the radius is the biggest and when the radius is 0. So we want to talk about maximum and 0 R values. Because it can be helpful to know when R is the biggest and when our graph goes through the pole. So I just want to do this by looking at an example. R equals 2 plus 2 cosine theta. And we want to find max R and when R equals 0. Well, what's going to make our radius? What's going to make R the biggest? When, well, the only thing that's changing is 2 cosine theta. So we want 2 cosine theta to be the biggest it can be. What's the biggest value that cosine theta can have? What is it? 1. We need the cosine of theta to equal 1. That's going to make 2 cosine theta as big as possible. Well, what is theta? Theta equals 0. So when theta is 0, R of 0 is 2 plus 2 cosine 0, which is 4. R equals 0 when, if I have R equals 0, what do I need to happen for R to equal 0? 2 cosine theta has to equal -2. So cosine theta has to equal -1, and theta equals pi. Any guess what this graph is? Well, we just graphed 2 minus 2 cosine theta, and it looked like this. It flipped over the vertical axis. So this is going to be something like this. And r equals 4. When theta equals 0, here on the polar axis. And r equals 0 when theta is pi over 2. Sorry, not pi over 2, pi. That's what we wrote right there. So from when theta goes from 0 to pi, r goes from 4 around to 0. And if I change this in my calculator, I change this to a plus, and I graph that. There we go. All right, questions there? All right, the last thing I want to talk about today, these are on your sheets, on your sheet that I gave you, but I want to talk about a little bit about special polar graphs. Now, what I would expect with special polar graphs is not that you have every single special polar graph memorized, but that you could look at an equation and say, oh, that's going to be a circle, or that's going to be a cardioid.
Or lemniscate.
Lemniscate, yeah, isn't that a nice word?
Yeah, yeah, infinity symbol.
All right. So anytime, let me stretch it a little more. There, it looks more like this. Anytime your equation is r equals something times cosine theta, or r equals something times sine theta, you're going to get a circle. The diameter is going to be a. And this, because it's a cosine function, polar axis symmetry. This, because it's a sine function, has pi over 2 symmetry. The lemniscate, you have an r squared. And this is the one that we simplified earlier. And it came out to be x squared plus y squared squared equals 2xy. So that's kind of a complicated equation. So these are lemniscates. The next family of special polar graphs are the limacons.
Yeah, wait, isn't it? Yeah, okay, I'm not right.
So those are limacons. So what I would expect is that you recognize when you have r equals a something plus or minus something cosine theta, or something plus or minus something sine theta, it's some kind of limacon. And depending on how a and b compare to each other, you get a limacon with a loop, a cardioid, a dimpled limacon, or a convex limacon, which just kind of flattens out. So those are limacons. And then the last family are the rose curves. So the rose curves, the difference between a circle and a rose curve, here we're multiplying theta by some number. So when this number that we multiply theta by is odd, we get the same number of petals as this number. So here is a cosine 3 theta. So we get 3 petals. Polar axis symmetry. Here this is a sine 5 theta. We have pi over 2 symmetry, and we have 5 petals. And a is the distance from the pole to the biggest value of r. When our number we multiply as even, we get twice as many petals. So here n equals 2, we get 4 petals. Here n equals 4, we get 8 petals. Yeah.
Is it possible to make that like they're not connected, I guess?
The petals?
Like yeah, in the center.
It is possible. The equations are more complicated.
Okay.
I had someone last year put a rose curve in their conics project. So they figured out in your program you have to turn polar mode on, and then they drew the rose curve, and then they turned polar mode back off so it could draw the rest of the graphs. And they had a nice flower made with a rose curve.
Wait, is that required?
No. But they wanted to figure out how to do it, and they did.
Well, then I might try to.
All right. Questions? Now, if you're interested, if you start graphing different polar functions.